Buenos días a todos. Les damos la bienvenida al seminario del grupo GESMAT. El día de hoy tenemos al profesor Abdelilah Benyoussef de la Universidad Mohammed V, que está localizada en la ciudad de Rabat, en Marruecos. El profesor Benyoussef se va a presentar, les va a explicar brevemente su trayectoria. Y su plática de él es Design of Nanomaterials for Hydrogen Production and Storage, Modeling and Simulation. Professor Benyoussef, very pleased to have you here. It's all yours, the presentation. Thanks.
Thank you, Dr. Felipe Caballero, for this introduction and for the invitation. It's a pleasure for me to give this talk. My talk is on the design of material and nanomaterial for hydrogen production and storage using modulation and simulation. It's well known that there is a need for an alternative fuel instead of fossil fuel for many reasons. For environmental concern, growing demand of energy, depletion in fossil fuels, awareness for equidistribution, and economy and processability. It's clear that the use of fossil fuel produce a negative impact on the environment by the production of greenhouse gases that make global warming of the earth, and then increase of natural disaster and melting of glacier and the drought and flood, and also acid rain and many other disasters are due to the greenhouse produced by fossil fuel. For that, it's very important to look for an alternative to fossil fuel, and the hydrogen is one promising element as alternative to fossil fuel, and this is in what is called hydrogen economy. Hydrogen economy means that the fuel is hydrogen, and also hydrogen is energy carrier. For that, there is a need to produce green hydrogen, that means from water, but also using renewable energy, not fossil one, without production, without emission of greenhouse gases, and then to store this hydrogen and to deliver it with efficient way, and then for application. Why hydrogen? Because hydrogen can be produced from diverse domestic resources and used for in multiple sectors. Hydrogen is the most abundant element. It's eco-friendly. Its combustion in air produce water only in addition to energy. And the hydrogen has the highest energy content by weight of all the known fuels, 3 times higher than gasoline. The use of hydrogen along with fuel cells or combustion-based technology can enable zero or near zero emission in transportation and other applications. Hydrogen can be used for gigawatt hours of energy storage. For that, the hydrogen economy is the economy of the future, with hydrogen as energy carrier and fuel. But to reach this target of hydrogen economy, there is a big connection between technology, logistics, and economy. Hydrogen as an energy carrier requires the development of optimal technology for the production, for the storage, for the delivery, for the conversion, and for the usage of hydrogen as fuel and as carrier. But that need, of course, a logistic, that means that need a network of hydrogen distribution, and that need investment to make this technology and to fulfill all the requirement for the development of technology, and also investment for this distribution network of hydrogen. Presently, most of the hydrogen is produced from fossil fuel, and this is not green hydrogen because it produces greenhouse gases. Most are produced from natural gas or from coal and also byproduct. Presently, most of the produced hydrogen is used for refinery and ammonium production. But in the future, if this target of hydrogen economy go well, then hydrogen will be used for energy production, for transport, and even as a gas for energy and heating. In addition, of course, of industrial need for ammonium, for refinery, and so on. The American Department of Energy fixed the K-hydrogen technology option for production, delivery, storage, conversion, and application in 3 terms: the near term, middle term, and longer term. For the near term, the production is based on gasification of coal or biomass, and also advanced fossil and biomass reforming, and also electrolysis at low and high temperature. But in the future, the technology, promising technology for producing hydrogen is based on advanced photoelectrochemical water splitting. I will give in this talk some example of how to produce hydrogen from photoelectrochemical water splitting. For the second technology to develop is the delivery. And for that, presently, most of the delivery of hydrogen is based on distribution from on-site production or tube trailers for gaseous hydrogen or cryogenic truck for liquid hydrogen. But in the future, the technology will be widespread pipeline transmission and distribution. For the storage, presently the hydrogen is stored as a gas by pressurized tanks, in pressurized tanks, or as a liquid in cryogenic vessel. But future technology of the future is based on storage of hydrogen as material-based hydrogen storage. I will give some example of material needed for promising for this storage. And the use of hydrogen need to convert this chemical energy stored in the hydrogen to electrical energy. And for this, there is a need for conversion using actually turbine combustion or fuel cells. And in the future, it will be fuel cells, combustion hybrid, or reversible fuel cells. And all this technology will help to make application in various domains, essentially utility system integrated energy system. In what follow, I will give example based on modeling and simulation to design materials and design materials, modeling and simulation. I will speak about density functional theory, molecular dynamic and kinetic Monte Carlo simulation. These help to make accordance between the properties needed for given application and the property of material even before the fabrication of this material. And this is obtained by a dialogue between experimentalists and theoreticians to identify the most promising material and devices related to energy conversion, storage, and sustainable environment. The outline of my presentation is based on two elements. I will focus on two elements: hydrogen production, about bulk materials, and nanomaterials. For nanomaterials, I will give example of 2D materials. And the second element in this presentation is the hydrogen storage, material-based hydrogen storage, and also I will give example of storage in a material, in bulk material, and then in storage in nanomaterials, especially 2D materials. For the production of, sorry, I have to move this. For hydrogen production, as I said before, it's obtained presently is obtained from fossil fuel, but using different techniques, catalytic steam reforming of methanol, coal gasification, partial oxidation of hydrocarbons, and other techniques. But the future and the promising techniques are techniques based on renewable energy by water splitting, water electrolysis, or photoelectrochemical conversion. I will speak about that. I will give some example of that. Thermochemical decomposition of water, photobiological process, and thermochemical process from biomass. But also hydrogen can be produced from nuclear reactor. Oh, sorry. I don't know why. Oh. Why? Sorry, I have to. Okay. Photocatalysis for hydrogen production is based on the use of a semiconductor that absorbs light and photogenerate a pair of electron and hole. The hole migrate and electron migrate to the surface of this semiconductor. The holes oxide water to produce oxygen, and the electron migrate to the surface to reduce the hydrogen ion and to obtain hydrogen molecule. But for that, photocatalysis material requirement is that the band gap of this material is higher than the redox potential of water. That means that the redox potential is inside the inside the band gap of the material. And we need to have, at the same time, a high band gap to be higher than the redox potential of water, but to be small to absorb visible light and not UV light. Many studies have been done for materials. They can be classified into 3 generations. The first generation is materials that absorb in the UV light. And the first element from this generation is titanium oxide. It absorbs in the UV light. But as you know, most of the solar energy is in the visible light, and to have a good performance of the material, we have to, the material with the semiconductor have to absorb visible light. For that, the second generation is generation of materials that absorb in the visible light, and most of these materials are obtained by modification of the first generation by doping, ion doping, or by semiconductor sensitization, or by our solid solution. I will give some example of the first and the second generation. The third generation is based on nanomaterials. Why nanomaterials? Because nanomaterials has very high specific surface, and that make this material very promising for photocatalysis. And also here there is 2D materials, 1D, 2D materials, 10 films, or 1D materials, nanorod or nanowire, and 0-dimensional nanoparticle. I will focus in this presentation on 2-dimensional material for photocatalysis, photoelectrochemical water splitting. The first example of material for photocatalysis is titanium oxide. It has been used for photocatalysis in 1972, and but it's absorbed in the UV light, as shown here. And this study has been done using density functional theory, and it showed that the density of state show a large gap, and also the absorption show there is no absorption in the visible light. How to make this material absorbing in the visible light and shift it from the first generation to the second one? Here an example of the doping and co-doping, doping of titanium by zirconium, and doping oxygen by sulfur. And what is shown here is that this doping can help to make a part of the absorption in the visible light. But as you see here, the band gap decrease, but it's the condition that the redox potential will be must be inside the band gap is not fulfilled for all the doping element. For that, there is a need to make some tanning of the pH of the aqueous solution in which the semiconductor is placed. I will give some example for that after. Other element from the first generation is the strontium titanium oxide. And this element have absorbed also in the UV light with a very large band gap, more than 3 electron volt. We have a direct band gap, and with he can be used as a photocatalyst because he fulfilled the condition that the redox potential of water is inside the band gap, but how to make it in the transformer it from first generation to second generation and absorbing the visible light is to make some doping. And here doping is by manganese for titanium and sulfur for oxygen. And it is shown that this material, the band gap decreases, are shown by the density of state and also by the band structure. And also this doping change the charge distribution. And for this material, R doping fulfill the condition of the redox potential inside the band gap, even for the co-doping or for one element doping, manganese or sulfur, and the absorption in the visible light is higher than for the pristine perovskite, strontium titan oxide. Other example is from potassium talum oxide, which is also perovskite, and it's absorbed in the UV light, but doping with vanadium and selenium can reduce the band gap and make this material absorbing in the visible light. And here we can see the contribution, the absorption in the visible light, and the band structure show that the edge of the conduction band is occupied by vanadium element with hybridization with oxygen. And to make this element, this material, good for catalyst, we have to change the pH of the aqueous solution. And as you see, I don't have can you see this for the co-doping, we have this condition of redox inside the band gap is fulfilled. That means this material can be a good photocatalyst for material. These three examples are examples of how we can transform a material from first generation that absorb in the UV light to absorbing in the visible light and making a good production of hydrogen and oxygen using only one element, one semiconductor. The second example is from material in the second generation. And this material is new materials, and it has been extensively studied for photovoltaic conversion. It's hybrid perovskite material, CH3NH3PbE3, and this material absorbing the visible light, but have a problem, disadvantage of degradation with water. If we put it in the aqueous solution, it is not stable. And for that, there is a need to make it more stable. And the idea I tell that in aqueous solution, we have to make encapsulation by two materials. And the idea is to make Z-scheme type 2 heterostructure with three materials. The first one is zinc oxide as transparent conducting oxide. And the second element is iron oxide. But this element, these materials absorb light also. And the calculation of work function may help to determine the Fermi energy and to have how the carrier charge move from this material, which is hybrid perovskite, to the zinc oxide, aluminum doped zinc oxide, which is used as transparent conduction material. And this material can make the reduction of ion hydrogen, because electron charge goes from hybrid perovskite to this electrode, while the Z-scheme type 2 heterostructure make the combination between electrons of the iron oxide and the holes of the hybrid perovskite, and then all the oxidation of water are made by holes from iron oxide. This material is stable in water, as shown by the molecular dynamic simulation, because with encapsulation, the heterostructure molecule water cannot penetrate into the hybrid perovskite, while for the non-encapsulated materials, hybrid perovskite, we have a water molecule inside this structure and it degrades it. And the charge transfer are shown by this Bader charge analysis, that charge from hybrid perovskite to zinc oxide and from iron oxide to the hybrid perovskite. And as you see here for the absorption is better with this heterostructure than this hybrid oxide perovskite. So this material which belong to the second generation have a problem of stability, chemical stability, but with this heterostructure, it is possible to improve that. For two-dimensional material, there are many studies for two-dimensional material. As you know, the first two-dimensional material discovered is the graphene, but graphene is not good material for photocatalysis because it is a semi-metal. But some material, 2D material, which have the same structure as graphene and which are flat as graphene, have a band gap and are semiconductor. An example of that is the graphitic germanium carbide, and this material is absorbed in the have absorption in the visible light, and it is dynamically stable, as shown by this phonon distribution. So semiconductor absorbing the visible light, good condition, stable, dynamically stable, and even with ions in the aqueous solution that improve its absorption because it reduces its absorption from 2 electron volt to minus to 1.5, 1.7, and it is good for absorption. And the third condition for a good photocatalytic is that the band gap contain the redox potential, and this is made by changing the pH of the aqueous solution. As you can see here, for pH equal 4, we have the best condition for a good photocatalyst. So this material is a good catalyst for water splitting. Another example is phosphorine. Phosphorine is a two-dimensional material discovered in 2014. It is not like a graphene. It is a semiconductor, not a semimetal. It is not flat like a graphene. It is a puckered with 2 layers and made of phosphorus. And this material has been fabricated first by exfoliation, mechanical exfoliation, but after that it has been obtained using different process. And here an example of solvent process for exfoliation of phosphorine from the black phosphorus, which is obtained from red phosphorus by using chemical vapor transport deposition. And the AFM image show some few layers of phosphorine, and also high resolution TEM show that behavior. It is obtained from black phosphorus, which is a layered material with a weak bending between layers. For that, it is easy to exfoliate it. It has been obtained and used, and has been also extensively studied theoretically using density functional theory, which confirm all the obtained experimental results, but also it has been shown that it has been shown that this material have very important properties. Among these properties, first, it is anisotropic. That means that there are 2 directions, zigzag direction and armchair direction, which these 2 directions have not the same properties. They have different properties. And it is a semiconductor with a direct band gap, which can reach for monolayer 2 electron volt. And it is, in addition to be anisotropic, this material is also asymmetric. That means that electron and hole have different mobility and different conductivity in the armchair and zigzag direction, but the dominant conduction and the dominant mobility is that of holes along zigzag direction. So for these properties, this material very promising for different application. Among this application, photocatalysis, this material has been a young material, but has been extensively studied by different groups. And the idea is how to improve the property of this material. Many ways have been done for that. I will speak about some of this. For example, changing the thickness of this material, change the property, the heterostructure change the property, the doping change the property, having nano ribbons or also change the property of this material. I will focus on some of this, first on the thickness. As I said before, to have a good photocatalyst, we have a material, semiconductor, must absorb in the visible light. For that, there is a need to change the band gap to absorb the visible light. And with phosphorin, when increasing the thickness, the band gap decreases. And as shown here, this is for one monolayer. By increasing the number of layers, the thickness, the band gap decreases to reach 0.3 for a bulk. So it is possible to choose the thickness that absorb in the visible light. Another thing is to charge transfer, injection of charge from the semiconductor to the co-catalyst in the aqueous solution. And for that, we have to turn the edge of the band, of the conduction band for electron, and the top of valence band for the holes. And this is also maybe controlled by thickness. The second, the third way to control property of this material is to control the Fermi energy. And for that, calculation of work function show that controlling the number of layers, controlling the thickness, the work function change from more than 5 to electron volt to some 4 electron volt. Also, the mobility is very important for this material and for the application. And as you see here, this is the mobility for one monolayer of hole, and this is the effective mass, which is very high, but for 2 layers, it decreases abruptly. And this is due to layer interaction and screening effect. And this is make this material, the control of this material for mobility, for charge injection, for light absorption, very useful. And it is a very robust material since it's still direct band gap semiconductor. This material can be, we can also control its property by strain engineering, strain by mismatch between the phosphorin and the substrate on which it can be deposited. And for that, it is possible, depending on the strain, direction of the strain, zigzag strain or partial strain, to decrease or increase the band gap, and also make a transition from indirect to direct band gap. And at the same time, it's possible to control the effective mass of this material in both directions, and a sharp decrease may be observed at this transition from direct to indirect band gap. Other effect of to control property of this material is stacking. As you know, the phosphorin is obtained by exfoliation of black phosphorus, or black phosphorus is a layered material, 3D layered materials. We can make one monolayer, but also 2, 3, 4, and so on. But the question is, are there only one stacking order, or there are many stacking orders? Reality is there is many stacking order, but the most symmetric one, there are 4 most symmetric stacking order, and the most stable is this one, EB stacking order. And they are all nearly stable, but the most stable is EB. This has been also confirmed by dynamic molecular simulation. And this material with few layers with different stacking have a gap between 1.4 for EB stacking and 1.1 for ED stacking. And charge battle analysis charge show the charge transfer between layers due to the nature of the stacking order. Another element important for phosphorene is how to control its pH of aqueous solution. For pH around 7 or 8, we have very good condition for photocatalysis because the bottom of the conduction band is higher than the redox potential, and the top of the valence band is lower than the oxidation potential. For this region, the H equal 8 is a good, 7 also, but 8 better, to have a good photocatalytic behavior of the material. And of course, if we increase the concentration of hydrogen ions or hydroxide ions, this condition is no more fulfilled. And the control of the pH of the aqueous solution in which this semiconductor is placed is very important. Another way to improve the behavior of phosphorene is by heterostructure, because it prevents the recombination of electron and holes, but also because substrate make a strain on the material. And depending on the substrate, here the decalcogenide materials, donor materials, and we can see that the power of conversion is improved by decreasing the donor optical gap, this gap. By decreasing the donor optical gap, we increase the power of conversion of phosphorene on material decalcogenide, but also by decreasing the conduction band offset, the decrease of conduction band offset also increase the power of conversion of this material. Phosphorene using heterostructure on decalcogenide, I reach 20% as power of conversion with 2% of strain compression. This is for the first part of my talk. For the second part of this talk is on the material for hydrogen storage. How to store hydrogen in an efficient way. How? Now, most of the storage is made by physical-based storage. That's mean as a gas or as a liquid. And for that, as a gas, we need a very high pressure. And as a liquid, we need very low temperature, 20 Kelvin. And cryogenic is very expensive and not safe. Why? The storage in material-based is very promising, but it depends on the nature of the material. Metal organic framework are material with a high surface area. It's a good material to store on the surface. I will give an example of this material. Liquid organic are materials that absorb hydrogen inside the liquid, but most studies are material in which the hydrogen is stored in interstitial site, like in interstitial hydride or complex hydride, and also chemical hydrogen, like in H3, BH3, or water, are material that can store hydrogen. What are the criteria to store hydrogen in a good way? The first criteria is appropriate thermodynamics. That means that the temperature needed to dissolve hydrogen from the material have to be around the room temperature, not very high, not very low. And the second criteria is the kinetic. That means that the quick uptake and release of hydrogen from the material. And the third criteria is storage capacity. Not very heavy tanks material and not very voluminous. The volumetric density must be high. And of course, long cycle lifetime for hydrogen absorption and deabsorption. Many material has been studied for that from water, but water, the temperature needed to desorb hydrogen from water is very high, more than 1,900 Kelvin, very high. It is very hard to desorb hydrogen from water by heating. But on the other side, here, metal organic framework have a very low desorption temperature. That means that it is very hard to keep hydrogen stored in metal organic framework, in MOF, because the desorption temperature is very low. At room temperature, the hydrogen cannot still adsorbed on the MOF. But in between, many other material with decreasing desorption temperature. One of the most studied material for hydrogen storage is magnesium hydride. Has been extensively studied, and this material, why it has been studied extensively? Because it's abundant element, its metallurgy is good, biocompatible, recyclable, and essentially because it have good gravimetric density, 7 weight %, as gravimetric is not very heavy material for hydrogen storage, and have good volumetric capacity, 110 grams of hydrogen per liter, but it still have two disadvantages. The first one is its kinetic is low. The time needed to fill the tanks is long, and to make it out is also long. And the second disadvantage of this material is its desorption temperature is high, around 500 Kelvin is high. We need to have a desorption temperature around a room temperature, 300 Kelvin. Many ways have been done to improve the performance, including nanomaterials and doping, allowing with other transition material. I give here some example of how this material has been improved for hydrogen storage. Here, example of allowing with for hydrogenation and dehydrogenation of magnesium hydride. If we make a substitution of magnesium by other element, titan, vanadium, chrome, and so on, what we can observe is that we have to reduce the adsorption energy. For that, we can decrease the desorption temperature. And for that, we have to reduce the charge transfer from hydrogen to the element, magnesium, and the doping element. And we can observe that this charge transfers decrease by doping different element. But essentially, what is the important parameter is the desorption temperature, which is 460, and it decrease for the allowing with different element, and it is around room temperature for chromium, 1/16 atom of chromium as doping of magnesium give the room temperature from 460 to 300, around 300. It's a good material. Also with niobium, we can obtain very good desorption temperature. So it's possible to make a good reduction of desorption temperature only by doping with element. But we see that doping with element, heavy element, decrease the gravimetric density, but not so much, because 7.6 and here 7.1 or 0.2, it's keep value high as the target of the American Department of Energy is to have more than 6, and here is 7. So it's possible to improve the storage of this material by doping with other elements. But we can also increase the gravimetric density by doping with light element. For example, by bore and lithium, if we make substitution of magnesium by bore and lithium, we obtain 9 weight percent, which is very high compared to magnesium hydride, which is 7. And at the same time, it decreases the desorption temperature. It's at the same time high gravimetric density and the desorption temperature around the room temperature. The second criteria, the second disadvantage of the magnesium hydride is its kinetic, it's slow. But here, with the substitution of different elements, aluminum, titan, vanadium, iron, and nickel, we see that the absorption time decrease, and the best element for allowing is nickel, that give a very fast absorption of hydrogen at 10 bar, and also better desorption of hydrogen at 1 bar. That means that this doping of magnesium hydride by other element can improve at the same time the desorption, the desorption temperature, it decrease the desorption temperature, it improve the kinetic, and also improve the gravimetric density. Other materials have been studied with magnesium. Here, example of the perovskite of magnesium and cobalt. It is a material that can absorb hydrogen. This material has the same disadvantage as magnesium hydride because the desorption temperature is around 500. And the advantage of this material is the volumetric density very high, 140, higher than magnesium hydride. The gravimetric is relatively low compared to magnesium hydride, but how to improve this desorption temperature? Here, an example of the way to make engineering strain to decrease the desorption temperature. As you see here, from around 500 for desorption temperature to 300 by making strain compression of the material. This is strain compression, this is strain expansion. And the better way to decrease the desorption temperature is to make a compression strain, which reduce the desorption temperature from 500 to only 300, which is the room temperature. And at the same time, the diffusion energy barrier decrease from 1.5 to 1.55 to 51. That means that the kinetic is better with strain than without strain for the pristine material, which is material perovskite. As I said before, organic metal framework are very good material for storage because they have a very high surface area, more than 2,900 square meter per gram. Is very high, very good. But this material have low, depending on the element, because you have a metal there. In metal organic, there is a metal. For zinc, the desorption temperature is 100, around 100. But if we make substitution of zinc by magnesium, the desorption temperature increases around 200. And for this metal organic framework, have 12 hydrogen, initial hydrogen, but it is possible to make molecule hydrogen adsorption in 3 sites: the cyclic side, the carboxylic side, and the metallic side. And the DFT helped to know which is the most stable site, and it is the cyclic site, which is the most stable. And this adsorption of hydrogen molecule on this side make the increase of the gravimetric from 1.5 to more than 6 weight percent, and at the same time increase the volumetric density from around 12 to 40. That means that this material, with the substitution of zinc by magnesium, is a good material for hydrogen absorption, and also the diffusion energy barrier are good from carboxylic to cyclic side that make easier the kinetic of this material. So the magnesium, better than the cadmium, better than the zinc, Mohammed V material. For two-dimensional material, as I said before, two-dimensional material are material with a very high surface area. The surface of material increase with increasing dimension. And from bulk 3 dimension to 2 dimension, the surface increase and the capacity of storage increase. And if we consider thin films of magnesium hydride, as I said before, magnesium hydride have high desorption temperature, around 500 Kelvin. By reducing the number of layers, the desorption temperature decreased, and it is around 380 Kelvin for few layers. That means that if we decrease the number of layers, the desorption temperature decrease, and it is possible to improve this behavior by strain. As you see here, compression strain make the material is less stable, and at the same time, the desorption temperature decreases. And even for the expansion strain, the stability decrease and the desorption temperature decrease. So we can improve the performance of the magnesium hydride by making thin films. Thin films store better hydrogen than bulk magnesium hydride. Graphene is also 2D material. We can think that it is good material for hydrogen storage, but graphene has one disadvantage, is its low desorption temperature. Its desorption temperature is around 57 Kelvin. That means it's very hard to keep hydrogen storage on graphene. I speak about molecule hydrogen storage, not passivation. And for that, other materials that have the same structure, flat, 2D, hexagonal structure, may be used for storage and are good material for storage. Among these material, borocarbide, aluminum carbide, zinc carbide, with very high gravimetric 10 for borocarbide, 11 for aluminum carbide, and 7 for zinc carbide. But the best advantage, the most important advantage is the increase of the desorption temperature from 57 to 215 and 205 for boro. And also the kinetic is good. For example, for boron carbide, the activation energy is 2.25, while for graphene is 14 millielectron volt. That means that this material are also promising for molecule hydrogen storage. I go back to the phosphorene as a good material for photocatalysis, but also for storage of hydrogen. DFT calculations show that there are many possible sites for adsorbing hydrogen molecule, and this hydrogen molecule may be stored as perpendicular or parallel to the plane of the of the phosphorane. At the most stable position is on the middle point of the bottom phosphorus bond, with the hydrogen molecule axis perpendicular to the phosphorane surface. And with this DFT calculation, we can show that the desorption temperature of phosphorane is around the room temperature, around 300 Kelvin. It's a very good thing. So this material can store hydrogen in a very good way with gravimetric density lower than that of magnesium hydride. But this material have also a good kinetics. It's the activation energy, depending of the position, is very low for bridge in the zigzag direction, which 0.3 compared to phosphorane, which compared to graphene, which is 14 millielectron volt. It's very easy, and the kinetic is very fast. The kinetic of hydrogen molecule on this material is very fast. So this material have a good gravimetric capacity, good desorption temperature around room temperature, and very good kinetic. And it is very hard to dissociate hydrogen molecule on the surface of phosphorane, because it needs very high energy. It's around 2.3 electron volts, which is very hard. So hydrogen is stored on the phosphorane as a molecule, not as atoms with chemisorption. It's absorbed as a molecule and as physisorption. So, in summary, density functional theory is a very useful method to design material for different application. Here I give 2 examples how what are the property for hydrogen production in a green way, as a green hydrogen using renewable energy and water splitting, and how to storage in a material, bulk material and 3D and 2D materials. And all this calculation has been done using density functional theory and the stability by dynamic, molecular dynamic simulation, and some result by kinetic Monte Carlo simulation. And thank you for your attention.